So, all right, anyway, good morning. Are you guys excited for the snow day? Yeah. Well, I am slightly excited, but it would have been nice to have known slightly earlier before I came into my office. But anyway, thank you guys for logging on here. You want to get home. Yeah, I understand, but it'll be safer later to leave. So the roads are not super good out there yet. I took the bus in, so I didn't have to drive myself here. So I want you guys to take a look at this example. And, you know, we talked at the end of class yesterday about, or on Wednesday, about where substituents would add in these directing effects. We had activators that were ortho-para directing, and we had deactivators, which were meta-directing. And I'm just going to go ahead and get my headphones to make this recording a little bit better. One second. There'll be less background noise and you might be able to hear me better. Maybe I'll hear you better. Okay, so what does everyone think? Is this substituent going to be an activator or a deactivator? And how do we know? All right, we have a vote for activator, activator. So what criteria do we look for? Lone pairs being able to be pushed into the ring, exactly. So we have a nitrogen atom connected here, and so this can be pushed into the ring to give several other resonance contributors. And there's a spectrum here of strong activators, moderate activators, and weak activators. This would fall right in the middle because this lone pair is also able to be delocalized into the carbonyl, and so that decreases the push into the ring because there's the competition with the carbonyl. So this would be an activator and therefore ortho-para directing. So when we treat it with something, let's treat it with Br2 and our Lewis acid catalyst, these conditions would give a bromination product, and that would look like this. We would get a mixture of para and ortho. And feel free to interrupt with any questions along the way. I'll try to check up with the chat here, and also you're welcome to just speak up. So you get a mixture of ortho and para here. There's no way to avoid that, and you would predict, though, that para, in this particular case, would be the major product due to sterics. So go ahead and mute yourself if you are not muted. All right, there, I took care of it for you. But there's a lot of background noise there. As I was saying, the para in this particular situation would predict it to be the major product because it would be most easily added there. This group is large enough that sterics would become an issue, and that would decrease the ortho product, okay? So if you look in your textbook on page 1006, there's a table of ortho-meta-para yields here just for a select subset of substituent groups, and it varies a little bit. The smaller the group, the more ortho you get, the larger the group, the more para you get, okay? So if you're ever producing an ortho product or a para product in synthesis, you can draw both, but just carry forward with the one that you're most interested in using. So any questions on how to think through this? Okay. Then moving on to slide 2. This just covers what we're going to talk about today, more on electrophilic aromatic substitution, how the directing effects play into synthesis primarily. So there is an exam wrapper available. There are some questions again about how you feel about chemistry and trying to see if the course has influenced that at all. So please be honest and take the time to answer those questions. It won't take super long. Homework 12B is due tonight. And then I just want to wish you all a happy Thanksgiving. I know the meme is missing. I'm sorry. Someone needs to make more electrophilic aromatic substitution memes, and I didn't have a chance to do that this morning. So I apologize. Maybe I can come up with 1 or 2 over the break. So that's where we're going today. And I just wanted to recap here on the next slide about those directing effects and why they are what they are. And we explain that with mechanism. So let's see, I should be able to point to things here somehow. Yeah, that's not what I wanted to do. I don't see the pointer. Aha, okay, got it. I'm on my iPad and the computer as well, so trying to make this work for me. Anyway, so we have ortho-para addition, add the electrophile. You get the same intermediates whether you add ortho or para, so hopefully you did try drawing out the para to see that for yourself. And the reason why ortho-para addition is favored when we have an activating group or a donating group is because of the additional resonance contributor here. More resonance, more stable. Therefore, this purple line, right, has a lower activation energy. And then for meta addition, we don't have that extra stability. So we have a higher activation energy and it's just a slower addition process, and ortho-para wins here. Okay, then it's a little bit less obvious here in the deactivating groups, but the idea is that this particular contributor that's boxed in red is destabilized. So we have this partial positive charge from a carbonyl group or really any other electron withdrawing group, deactivating group that is a resonance withdrawer, especially this partial positive charge next to the formal positive charge in this contributor. This is destabilized, so it's higher in energy. That makes the ortho-para addition much slower. The meta addition is preferred here. So this is a situation where with an activator, the ortho-para addition is stabilized, the intermediate there is stabilized, and with the deactivators, the ortho-para addition is destabilized. So that's how I would frame it. And just the list that I tacked onto the end of the slides from Wednesday's class, this is a table from the book. We have activators, which are those groups with lone pairs or alkyl groups, okay? And then we have the deactivators, the halogens, which are inductively withdrawing. And then the resonance withdrawers are the carbonyls and other species down here. The ortho-para directors are the activators with the exception of the halogens. So the reason that halogens are still ortho-para directing while they are deactivating is that that sigma complex can be stabilized by resonance. So try drawing out the ortho-para addition for a halogen substituent and see that that sigma complex can be stabilized. You get a fourth contributing structure by donating lone pairs in. So these are still functioning as resonance donors to stabilize that sigma complex, but the halogens are less reactive than benzene. Therefore, it's deactivated. So the rate of the reaction of, say, chlorobenzene is slower than benzene. So we know that the ring is deactivated. That means they're functioning as withdrawers, but they direct orthopara. So how do we explain the data there? Well, they must function as resonance donors, okay? So I see some crazy stuff happening on the videos over there, but I will keep going. Any questions? All right, silence is good, I suppose. All right, now let's look at this. This is part of what I think is so cool about this unit. All right, so how do we take benzene and make para-bromonitrobenzene or meta-bromonitrobenzene? Can anyone think or jot down, if you're taking notes, of how you might carry out these two syntheses? So we've got two groups on there. One relationship is para, one relationship is meta. Let's say you want to make the para product here. Which group are you going to add first? Okay, Marta says we'll add the activator first, and Tess said about adding the BR first. So you want to consider your substituents. The BR is an orthopara director. The nitro group is a meta director. And if you want the ortho or para relationship, then you must add that directing group first. So we would first treat this with Br2 and iron tribromide, the Lewis acid catalyst, and follow that with the nitration conditions, HNO3 and sulfuric acid. All right. And as you can tell then, trying to make the meta product, you'd want to consider, again, the directing effects of each substituent. The nitro group adds meta, or will force another group to add meta. So we'll add that one first, HNO3 and sulfuric acid, followed by the Br2 iron tribromide. So the order of the reactions is important here. That's the takeaway from this. You have to pay attention to the directing effects of your substituents and the product that you want here. So I have a more complex scenario on this slide. So what are the directing effects of each substituent here? What's the directing effect of the OH? Caroline says the OH is an orthopara director, which is true because we have the lone pairs to push in there and stabilize that sigma complex intermediate. All right, and what's the effect of the BR? Udasi says that the BR is orthopara, which it is, right? Keep in mind this is the exception. It is a deactivator, but it still does direct orthopara. And we can keep that in mind based on the fact that there's lone pairs here that can be pushed in. So this is somewhat of an issue, right? Because we have two orthopara directing substituents, but we have a meta relationship between these two groups. So now what? Well, let's think about ways that we can make phenols or aryl bromides. How do we make phenols? Does anyone remember? Take that as a no. So phenols can be made from nitrobenzene. And if we reduce the nitro group to an amine, which I showed you can be done with tin, an acid, followed by NaOH. The book also uses just zinc and HCl, which would also have to be followed by NaOH to get the neutral amine out there. You can do this under hydrogenation conditions with H2 and a metal catalyst. So there's a variety of reductions that can transform a nitro group to an amino group. I just want you to be aware of that. And then we can take that amino group and turn it into a diazonium salt. That is the N triple bond N group here that we highlighted on Monday, I guess it would have been. And this is carried out with NaNO2 and acid. And from the diazonium is where we have access to a number of other functional groups. We can treat this with copper 1 salts of halides and make bromides and iodides and fluorides. We can treat it with water and heat and make phenols. So if you see a phenol, this is the only way that you know how to make one, this series of 3 steps. And we make aryl bromides. Of course, you can make those from diazonium salts if you use copper bromide here. And we can also take benzene and treat it with the standard conditions to give FeBr3, to give the aryl halide. Okay, so we know how to make phenols, we know how to make aryl bromides, so how do we combine this and get the meta substitution pattern? Can anyone see what we would want to do first? Wouldn't we want to add the HNO3 first, add the nitro first to get the nitro? Great, yes. So we want to add the nitro group first so that we get a meta director on there. Then we can add the bromine and the appropriate orientation. Whoops, that's NO2, undo, undo. And then follow it with the appropriate steps to get the phenol. Okay, so you have to think about ways to make the functional groups on that path. Hopefully, I wouldn't give you something that couldn't be made, but you have to think about the ortho versus ortho-para versus meta addition of those substituent groups. Okay, are there questions about this? There's a variety of ways to, give you examples like this. You could imagine having a para relationship between two meta-directing groups. And, well, that's maybe less easy to do, but there will be something like this on your fourth test where you have to take benzene and make something through a series of steps. And so this may be part of that thought process. Any questions before we move forward? Okay, so I already wrote all that out. And that more or less sums up what I wanted to tell you with respect to applying these reactions in synthesis, right? And so we're switching gears now. We were talking about the Friedel-Crafts alkylation and acylation on Monday, and we know that we can add alkyl groups to benzene with alkyl chlorides. You could add alkyl bromides. It's mostly chlorides for whatever reason. And then some Lewis acid catalyst. It can be iron trichloride, aluminum trichloride, whatever. And then we can also do the similar process for acyl chlorides. Remember, this can be any R group, and this is an acyl group. And I'll just throw in aluminum trichloride here to show you that that's usable. And we put our R group on here. So can anyone remember what the electrophile is for the alkylation reaction? The alkyl group, yes, that is true. What about the alkyl group makes it an electrophile? The carbocation, exactly. So we have this type of intermediate that ultimately generates this ion pair with the carbocation and the FeCl4 minus, right? So the carbocation is the electrophile. What does this mean about the limitations of Friedel-Crafts alkylation? Right, we have rearrangements. And must be in acidic conditions. So sometimes, yes, there certainly are examples in the book where you can generate carbocations under acidic conditions, such as on pages 1004 and 1005. These conditions that we're looking at here are Lewis acid conditions, so they're not the Bronsted acid conditions that we are familiar with, but the Lewis acid here is strong enough to generate the carbocation intermediate. So yes and yes. What about trying to attach something like a methyl group on there? Could we treat benzene with methyl chloride and get toluene? The cation would be CH3 plus, right? A methyl cation. If you recall the ranking of carbocation stability, methyl cations are the highest in energy, even higher in energy than primary carbocations. And so as a result, this is limited. We cannot make primary linkages to rings, right? So as an example, if we take propyl chloride and aluminum trichloride as the acid catalyst, we end up getting isopropyl addition because that primary carbocation undergoes a rearrangement to give the more stable secondary carbocation. You can see it happening almost as a concerted step. If you think about the electrophile here being this, and we could have a hydride shift occur at the same time that leaving group leaves, and you get then the isopropyl cation and AlCl4 minus. So this does not work to make primary linkages. Think of another way to make toluene. You have to apply one of those other carbon-carbon bond forming reactions. Friedel-Crafts is not efficient for this reason, and one other reason we're getting to make methyl or primary linkages to the aromatic ring. And I've cluttered up this slide enough, but does the same apply to acylation? Do these acyl cations rearrange? And you may not obviously see this, but it is a resonance stabilized cation. And so the answer to that is no. There are no problems with rearrangements or destabilization of any particular type of acyl cation. Acyl cation more or less is the same for any Friedel-Crafts acylation. Any questions? Just making sure that people have enough time to type here. So I'm pausing what feels like a long time. So since we can't make primary linkages, how can we do that? How could we take a benzene ring and add to it, let's say, the propyl group? Well, this is where we can take advantage of another reaction. We can add an acyl group to this. To attach the 3 carbons, and then we can use a reduction. This is a particular reduction step known as the Wolff-Kishner reduction. This mechanism is a nucleophilic addition mechanism that is covered in the second semester. So I won't go through the mechanism with you here, but it effectively replaces that carbonyl oxygen with 2 hydrogen atoms. So the name reduction implies that we're increasing the bonds to hydrogen, reducing the bonds to oxygen. And this Wolff-Kishner reduction will do that. And this gives us then access to that primary linkage on the aromatic ring. And notice here, synthetically, we have a meta-director with the carbonyl next door, and we do the Wolff-Kishner, we have an ortho-para director. So synthetically, this reaction becomes useful too in terms of thinking about, okay, if I want to make something like the meta-bromo propylbenzene, I can do the Friedel-Crafts acylation, follow it with the bromination, then do the Wolff-Kishner to give me the alkyl group. Okay, and all of these reactions that we've been talking about will be put into reaction webs. I hope to make a reaction web, immediately after this class, and then share that with you so that while you are studying over break, which I know you all will be, and I encourage you to do just a little bit every day. You can take Thanksgiving Day off, but just do like 15 minutes of organic chemistry. Do a book problem or two. But if you don't do any organic chemistry between now and next Monday, then I don't want to see what happens after that. I think it will be detrimental. If you're not using it, you lose it, and that is going to play out. And with our exam so close after the break, I don't want you to forget all that you know. So anyway, are there questions about how to use the Wolff-Kishner at all? There are alternatives to the Wolff-Kishner. So these are basic conditions. And so if you happen to have, and we don't get into this, so I'm just giving you some backstory, but these are basic conditions, obviously, with NaOH there. There is the Clemmensen reduction, which is done under acidic conditions with zinc mercury amalgam. So it's a mixture of zinc and mercury, and then HCl is thrown in there. And so this does the same thing as the Wolff-Kishner, but under acidic conditions. So we have these complementary reactions that have different conditions here. So in case you see that, but either one of them will work. Okay. And moving along. There are 3 problems with the Friedel-Crafts reaction. We're looking at all 3 of them right now. The first one was the fact that primary linkages cannot be made, and we have that problem with rearrangements. So the second problem is that we get polyalkylations, that when we add, say, isopropyl chloride and aluminum trichloride, we get addition not once, but twice, or even 3 times or 4 times here, depending on what your alkyl group is, of course. The size will have some rate determining aspect to it. But what could you use to explain the fact that after it adds once, we can't stop it from adding again? How could we explain that? I want you to think about the reactivity of benzene compared to the alkylated benzene. Which one is more reactive? Is benzene more reactive, or is alkyl benzene more reactive? Why do we think the alkyl benzene is more reactive? Yes, it's an activating group, exactly. It's an inductive donor. So this is activated, and activated rings are more reactive than benzene. So this is another reason why you can't make toluene very well from benzene, because that methyl group, relatively small, and now that ring is more activated, so it will undergo these polyalkylations. And as Anushka asks here, the products are more reactive than the starting reagents. Yeah, exactly. So you can think of this, and I'm going to use my hands here, and I don't know that the recording is going to pick up my video, but if you can see it from your end. So you have benzene and you have your alkyl benzene in solution, right? Because benzene is producing alkyl benzene and you have a mix of both. And what has to happen for a reaction to occur is that the aromatic ring must find the carbocation that's produced here. And because the alkylated benzene is more reactive, when that collision happens, it's going to be an easier hill to get over, a lower activation energy. And so that is what's happening in solution. It's just more reactive, more easily able to form product there. So a way around this is to use an excess of benzene. And that means there'll be so much benzene around that the probability of an alkylated benzene finding the carbocation is just going to be much, much less than benzene finding the carbocation. So benzene is often used as a solvent here, and of course you could separate the benzene from the monoalkylated product relatively easily there. So that's one way to do this. And I will say that we will just assume that we are doing monoalkylations unless otherwise specified. Okay, so assume monoalkylation unless otherwise specified. But there are conditions, for example, using excess benzene, that would minimize the polyalkylated products. Go ahead and type any questions if you have any. I'm going to click to the next slide here. And just, thinking about the same ideas with the acylation, why don't we observe polyacylations? Yeah, we have a deactivated ring because the new group that has been added is a resonance withdrawing group. Okay, so we don't observe polyacylation, no problems there. All right, so I just wanted to highlight that. And we have just one more slide, I think. Yeah, so the Friedel-Crafts alkylation and acylation cannot be carried out on moderately or strongly deactivated rings. So what this means is that we cannot take a nitrobenzene and do the Friedel-Crafts on it. There is no reaction. So this plays out in synthesis in a way. You have to pay attention to what group you add first, because the Friedel-Crafts alkylation and acylation cannot be carried out on deactivated rings. So the only deactivated ring that it can work on is the halogenated ring. It is not deactivated enough, but essentially the idea here is that carbocation intermediate isn't a particularly good electrophile compared to some of the other electrophiles that we're generating, the nitroso cation and the whatever you want to call the bromine or chlorine electrophiles that are generated with those Lewis acids, okay? So there are limitations, 3 limitations. 1, no primary linkages and rearrangements. 2, polyalkylations with the Friedel-Crafts alkylation. And then the third is that it cannot be carried out on deactivated rings. So be careful with the order of the reactions that you are using in synthesis. And just to be sure, yeah, so the next couple slides are clicker questions that I will, you'll need to give me some time, but I got to put them into Canvas and just let you test yourself there on a few of the things that we talked about today. And there'll be 3, I have at least 3 in there, and there I may throw in a 4th one. So 3 or 4 questions just to give you a chance to test yourself on these concepts. And we will come back on the Monday following the break and more or less have a review catch-up day, and we are pretty much caught up, so it'll be an opportunity for us to practice using these. So I will try to put together some practice problems for us to do and work through those with the team during class as a way to get ready for that exam on Friday the 30th. So I'm going to go ahead and stop the recording at this point, and I'll stick around here if anyone wants to chat